just see if my, okay, yes. So today I'm going to be talking about the Bershadsky-Polyakov vertex algebra. So just a quick word of introduction and context. So Bershadsky-Polyakov vertex algebra is a type of W algebra. So in the past couple of years, we have seen a lot of research about W algebras, and I personally find it very interesting. And there's lots of rich structure here, connections with physics, with number theory. And yeah, I think it's an exciting research area right now. There are lots of types of W algebras, and we have finite and affine W algebras. And then in the affine world, we have principal, minimal, subregular W algebras, which correspond to the type of nilpotent element used in the construction. And this algebra that we're working on, the Bershadsky-Polyakov algebra, is a type of minimal affine W algebra. So how is it constructed? So it's obtained from the affine vertex algebra via a homological construction known as the quantum Drinfeld-Sokolov reduction, and it corresponds to a minimal nilpotent element. So this Bershadsky-Polyakov vertex algebra is one of the simplest examples of minimal affine W algebras, affine W algebras in general. And what's special about minimal affine W algebras is that there is a structure result about them. So we know how they are generated. We know the generators and a type of relations called lambda brackets. So by a result of Katz and Wakimoto, I believe, we know that minimal affine W algebras are strongly generated by vectors, a set of vectors of conformal weight 3/2, then a set of vectors of conformal weight 1, like the Heisenberg vectors, and the Virasoro. This type of result is not known in general for other affine W algebras, which makes them much harder to study. And yeah, so this is why it's kind of natural to start with minimal affine W algebras. Okay, so for non-critical level K, the universal affine W algebra has a unique simple quotient. Okay, so if we take the Lie algebra G to be SL3 and we take the minimal nilpotent elements, then we obtain the Bershadsky-Polyakov vertex algebra. And basically, this is one of the two we could get from SL3. The other one is the so-called homological vertex algebra, which corresponds to the principal nilpotent element. Okay, so from the structure theorem that we saw before, we know that the Bershadsky-Polyakov algebra is generated by four fields. We have two generators, G plus, G minus, of weight 3/2. We have the Heisenberg J, and we have the Virasoro T. So this algebra, in its original form, is Z-half graded. This is something which holds in general for non-principal affine W algebras. But if we choose a new Virasoro vector of this form, so we add to the old Virasoro 1/2 derivation of the Heisenberg, then we obtain a Z grading on our vertex algebra. And yeah, so from the OPE relations, we get the following commutation relations for the fields Lj, G plus, and G minus. So we'll be interested in the representation theory of the Bershadsky-Polyakov vertex algebra. And yeah, so we use, in our studies, we use the W algebra, which is of course an associative algebra, which is special in the sense that there is a one-to-one correspondence between the irreducible modules of the W algebra and of the VOA. Okay, so the irreducible WK modules are generated, so we will study mostly highest weight modules, which are generated by a highest weight vector. And this existence follows either from the Drinfeld so-called reduction functor or from the Zhu theory. And yeah, we will exploit a few nice symmetries between irreducible WK modules. So here we have one of them, basically using the theory of contragradient modules. We see that Lxy is a WK module if and only if L minus 6 y plus x is a WK module. We will later also use another symmetry using the so-called spectral flow automorphisms. Okay, so just a bit of context. So for the representation theory of the Bershadsky-Polyakov vertex algebra, I believe it was first studied by Tomiyuki Arakawa, who published the result in 2013. And he proved that for half integer levels, k, the Bershadsky-Polyakov vertex algebra is rational. Okay, and in his paper, he used a special class of associative algebras called the Smith algebra. And we kind of went in that direction and also exploited properties of this associative algebra. So what we do here is we look at the Zhu algebra associated to our vertex algebra, and when we change the Virasoro, we get that the Zhu algebra is actually a quotient of another associative algebra, of this Smith algebra. Okay, and what is the Smith algebra? This is a type of algebra which is kind of similar to the universal associative algebra of universal enveloping algebra of SL2. So here we have generators EF, X, and Y, and the following relations. These algebras are parameterized by the polynomial G. Okay, and we have these relations, this sort of commutation relations. And these associative algebras have been studied, I believe, in the 80s independently. I mean, not related to vertex algebra, algebra theory. And there's a lot of theory developed already for them, like the highest weight modules, category O, and so on. And the authors found interesting that they do, they share a lot of properties with the enveloping algebra of SL2. Okay, and so we generalize this original definition a bit by adding a central element, y, so that we could have this polynomial in two variables here. Okay, and what happens is that for a special choice of the polynomial g, it turns out that the W algebra associated to the Bershadsky-Polyakov vertex algebra is isomorphic to a certain quotient of the Smith algebra Rg. This polynomial here comes from commutation relations in the vertex algebra. So it comes from where it is from this relation here for the commutation relation between G plus and G minus. Okay, and then we can use properties of the Smith algebra to study representation theory of the Bershadsky-Polyakov vertex algebra. Okay, and a key part of this work are these functions here, these polynomials hi in two variables, which are defined in this way. So we have 1 over I and the sum here of polynomials gxy and so on, gx plus 1, y, and so on. So this is a certain quadratic polynomial. We have x squared here and y, and it turns out, so a property of the Smith algebra is that the modules for the Smith algebra are in one-to-one correspondence with zeros of these polynomials here. Okay, so we kind of exploit, not exactly this, but very similar. And we exploit this property in order to classify modules for the Bershadsky-Polyakov vertex algebra. Okay, so Arakawa proved in his paper this nice lemma here. So basically, if the top level of our highest weight module is n-dimensional, then it holds that the nth polynomial hn of xy is equal to 0. Okay, and then so using this delta operator here, which produces a family of automorphisms, we obtain this nice symmetry result. I mean, this is result by Arakawa, but it's really integral to our work. What happens here is that if we take suppose that the top level of the module has dimension y, and we act with this delta operator. Also, these operators are also called spectral flow automorphisms to get a new sort of highest weight. Then we get that the module L with highest weights x hat y, x hat I, and y hat I is isomorphic to the spectral flow image of the original module LXY. Okay, so now we come to the positive integer levels WK. So we started studying these highest weight Bershadsky-Polyakov algebra modules a few years ago, and the first thing we noticed is that we have these expressions for singular vectors for integer n, and these are basically the same as those that Arakawa has in his paper for half integer levels. And yeah, so we notice that these are also singular and computed and proved this via computation. And then sorry. And basically, once we had these expressions for singular vectors, we were able to obtain a certain necessary condition for WK modules. So basically, what we see is that if something is WK module, then its highest weight needs to satisfy a certain relation HI XY equals 0. So those highest, so if something is a highest weight module, then the highest weight needs to be 0 of a polynomial HI. Okay, this is actually easily obtained from the singular vectors, and of course using those results by Arakawa. The hard part was showing that these actually are WK modules. And we were able to prove that these in fact are all WK modules. And so how do we look at this? So we need to construct a family of irreducible WK modules which satisfy HI of XY is equal to 0. So how do we do this? So we rely on the spectral flow construction of WK modules, which is just to say that we exploit this symmetry, which says that if we have irreducible module for the Bershadsky-Polyakov algebra, and we act with the spectral flow automorphism, we get another module. So we do this in a couple of steps. First, we start with what we know is a WK module, which is WK itself, or L00. And then we apply this spectral flow automorphism to obtain a countable family of highest weights for which we know that they will satisfy these conditions. Okay, so basically we start from L00, and then using that symmetry result, we compute just how this next points need to look like, and we obtain this recursive relation for which it holds that for every solution xn yn is it holds that L xn yn is in fact an irreducible WK module, and they are connected to L00 in this way. And also by construction, it holds that these points are that they are in fact zeros of polynomials h1 and hk plus 2. Okay, so this is elementary. I mean, we start from L00 and then just keep going and obtain this family of highest weights. So we do this in one direction and then in other directions. So we do this for n greater than 0 and for n less than 0. And in this way, we obtain like a family of simple current modules. Okay. But now, so we know that we have an infinite family of modules, but we still don't know that, in fact, for any 0 of the curve h1 or hk plus 2, that Lxy is in fact a WK module. So how do we fill those gaps? The idea here is like a sort of algebraic continuation. So what's the basis for this is that the W algebra is a certain quotient of the polynomial algebra in two variables, and since it's Noetherian, then we know that this ideal must be finitely generated, generated by finitely many polynomials. Okay, and since we know that these finitely many polynomials in one variable already have infinitely many zeros, then it follows that they must be identically equal to 0. And in this way, there's a bit more technicalities here, but this is basically how we can conclude that for if xy, if it holds that h1 or hk plus 2 of xy is equal to 0, then the module Lxy is an irreducible ordinary WK module. Okay, so in this way we have covered the like the extremal situations, the h1 and hk plus 2. And we still need to prove that also for all the curves in between, for general hi of xy, it also holds that the zeros are really highest weights of a WK module. So we do this by basically referring back to hk plus 2. So we just find a point for every I in between 1 and k plus 2. We find a point so that hi of this point is equal to k plus 2 of this point, which we know is equal to 0. So what do we get from this? We get 1 point for which we know we have a pair xy yi for which Lxi yi is in fact a module. And once we get this point, which we know is the highest weight, then we can do the same construction we had before, do the recursive relation by acting with the spectral flow automorphism, and then we get in the same way this infinite family of points. So we do the same thing, because here the crucial thing was that we started from L00, which we knew to be a module, and then this enables us to get other modules. And here we get this point, okay, from which we can start, which we know to be a module, and that which then gets us other points. Yeah, those first constructions, these constructions, they got us the zeros of h1 and hk plus 2. And then with this point, that was from L00, and then with this point we get all the zeros of curves in between. So for I between 2 and k plus 1. Okay. So now we kind of do the same thing, because now again we have an infinite family of WK modules, such that hi of these points is equal to 0. But we still don't know that generally for each point of the curve HI, that Lxy is in fact a module. But this is, again, we use the same idea as before. We use the property of the W algebra, and yeah, basically we need to have, we get that we have finitely many polynomials which have infinitely many zeros, and then they all need to be equal to 0. And this gets us that, yeah, that for each point of the curve HI, we have that Lxy is a WK module. And yeah, so this is this is kind of the idea of the proof, and we get that if HI of xy is equal to 0, then Lxy is in fact an irreducible ordinary WK module. So this was the other direction in the theorem, and yeah, in this way we were able to have a classification of WK modules for positive integer levels k. Okay, so now I will give a few examples. Probably the easiest one is k minus 1. So this is k minus 1 is a special level. This is in fact a collapsing level for the Bershadsky-Polyakov vertex algebra. And in this case, it actually holds that W minus 1 is just isomorphic to the Heisenberg vertex algebra. And yeah, then since we know how the modules for the Heisenberg vertex algebra look like, then we can just compare it to our theorem. And yeah, in fact, all reducible W minus 1 modules are these. So Lxy such that xy is a 0 of the polynomial h1. The situation gets more complicated for k equals 0. So here, in this case, we first obtain a realization of the Bershadsky-Polyakov vertex algebra W0. And here we do actually sort of a bosonization of a known result where W0 was realized as it was embedded in the tensor product of Clifford and symplectic fermions, and here we use this result to get a realization as a certain subalgebra of a lattice VOA. Okay, so we take this lattice VOA here and consider a certain subalgebra of this lattice VOA. And then we know that these are the irreducible VD modules. And so what holds here is that W0 can be realized as a vertex subalgebra VD in this way. And then using this realization, it's just computation to see that the modules for W0 do in fact satisfy these conditions. So they are all the modules are those which are which highest weights are zeros of polynomials h1 and h2. Okay, so another example would be W1. I will get to that, but first I want to talk about another nice property of W1, which is that it has a sort of Kazama-Suzuki type duality relation with the vertex superalgebra OSP 1,2 at level k minus 5/4. So generally, if U and V are two vertex superalgebras, we say that V is the Kazama-Suzuki dual of U. If we have two injective homomorphisms, so that phi1 goes from V to U tensor F, and phi2 goes from U to V tensor F minus 1. Here, F is a certain Clifford vertex superalgebra, and F minus 1 is a lattice VOA, super VOA, which is associated to the negative definite lattice, Z minus 1. Okay, yeah, and it holds that the vertex superalgebra V is isomorphic to the commutator of H1 in U tensor F, and U is isomorphic to the commutator of H2 in V tensor F minus 1. Here, H1 and H2 are Heisenberg vertex subalgebras of U tensor F and V tensor F minus 1. Okay, so basically what holds here is that affine vertex superalgebra, LK of OSP 1,2, is the Kazama-Suzuki dual of the Bershadsky-Polyakov vertex algebra V1, W1. Yeah, for this level, K prime equals minus 5/4. So we show this by constructing two explicit embeddings, and we also study properties of modules and their relations. So in fact, using free field realization of LK OSP 1,2 obtained by Dražen, we see that they are, in fact, that the relaxed modules for LK OSP 1,2 are mapped to ordinary W1 modules. Okay, so yeah, quickly, the OSP 1,2 is a simple complex Lie subalgebra satisfying these anti-commutation relations. And here we use the Sugawara conformal vector. And what is really important here is that there is a conformal embedding of LKSL2 into LKOSP 1,2 at level K prime equals minus 5/4. Okay, and using this, we can construct a certain homomorphism of vertex algebras. One homomorphism phi, which goes from W1 to the tensor product of L minus 5/4 OSP 1,2 tensor the Clifford vertex algebra. Okay, we do this. Yeah, we construct explicitly this the generators, and we show that in fact the image of this homomorphism is isomorphic to the simple quotient, W1. Okay, and also what's interesting about the modules. So the tensor product of the L minus pi over 4 of OSP, tensor F, is isomorphic to a direct sum of the modules for the Bershadsky-Polyakov algebra W1, tensor modules for the Heisenberg algebra. And yeah, and then we conclude that W1 is isomorphic to the commutator of the Heisenberg vertex subalgebra of L minus 5 over 4 of OSP 1, 2 tensor the Clifford vertex algebra. And we also can go in the other direction and construct a homomorphism of vertex algebras, which goes from L minus 5 over 4 of OSP 1, 2 into the tensor product of W1 tensor F minus 1. This F minus 1 is the lattice VOA associated to the negative definite lattice. And again, yeah, we explicitly define the generators, and we have these properties of modules, so that W1 tensor F minus 1 is isomorphic to the direct sum of this action of the spectral flow automorphism for OSP on OSP at level minus 5 over 4 tensor the Heisenberg vertex algebra. And yeah, we can conclude that the L minus 5 over 4 of OSP 1, 2 is in fact the commutator of the Heisenberg vertex algebra in the tensor product of the Bershadsky-Polyakov and F minus 1. Okay, yeah, that's all. Thank you for listening.